Okay. So this is the last new material before the test. Wednesday will be a review. So if you haven't looked at the practice test that's on the lectures page of the course website, please do, so that you can have questions ready for Wednesday, because Wednesday we're going to be focusing on the practice test and also take some time to list, okay, here are the kinds of problems that will be on a real test, and a general approach for how you deal with them. Okay. Now, let's see. Okay, so for today we're going to look at equations, among the simplest that we've seen so far, linear equations that have constant coefficients. So we actually already have a solution formula, but now this is about how we work with that formula to answer certain questions that come from applications. So for all the examples that I'm going to go through today, we have this ODE, where A and B are constants. Okay. And we have some initial condition at time t equals 0. Now, I won't go through the process of here, because it's something we've already been over. Suffice to say that how you would solve it is use an integrating factor, and in this case, the integrating factor would be e to the minus at. So then everything can be worked out, all the integrals can be worked out, and here's the solution that you get. So we have first values taken into account, e to the at, y naught. And then we have a second term that takes b into account. So that's e to the at minus b. And times b. Now, if you can, what I would recommend is try to simply remember this solution formula. You don't absolutely have to, because given this equation, you don't know this, you can always just go through the motions of using its integrating factor and working it out that way.
So why is it that the e to the negative at results in the
Because what happens, so if I write it this way, and then multiply both sides, then the left side becomes e to the minus at times y, all prime, equals e to the minus at b. So then what happens is you'll integrate both sides, and so you'll have e to the minus at over here. But you want to solve for y, ultimately. So, all right, so you have e to the minus at y is equal to the integral of e to the minus at dt all times b. I've already pulled out b because it's a constant. But then what do you do next? You multiply both sides by e to the plus at.
What happened to the minus ay times e to the?
Sorry, what?
What happened to the? So presumably we get the e to the negative at all that prime.
Yeah.
The first part is the multiplication with the parentheses. What about the multiplying e to the negative at by minus ay?
Oh, you're going from here to here?
Yeah.
Yeah. Well, because of a prime. If I take the derivative of all this, product rule. So you get e to the minus at y prime over here, and then you get y times the derivative of e to the minus at, which is minus a e to the minus at. So that's where that comes about. So what I'm doing in going from here to here is like you're undoing the product. And then I need to isolate y, so I have to multiply both sides. Okay. And what will happen from here is when you work out this integral, then you get b e to the minus at all over minus a plus a constant. And then if I distribute the e to the at throughout, then I get minus b over a plus c e to the at. Okay. But then, if I substitute t equals 0, then I have this plus c is equal to must be equal to y naught. So now I have c is equal to y naught minus b over a. So then I can take that and substitute that in here. Once you simplify everything as much as you can, then this is what you end up with.
Is it plus b over a?
Sorry, what?
Is it plus b over a?
Yes. Your questions before we go to applications? Okay. So in fact, multiplying this out, we have a minus b over a. That's already here. And then e to the at y naught plus b over a leads to the other term. Okay, but what we're going to do now from this point is whatever application and therefore DE in this form that we're presented with, we can just jump directly to using this to solve whatever problems related to that. And so over time, I'd see this formula come up so often that I just end up remembering it. That comes in handy. Okay. Now, one case that comes up in simpler models is when b is 0. So in that case, we have y prime equals just ay. Y of 0 is y naught. And so then the part of b I could just drop out of the solution formula. And we have that for our solution. So again, this is the simplest DE we deal with all semester long. Again, it's wise to just learn dissolution formulas that you can use it right away instead of going through. This is a separable and linear equation. You could solve it either one of those ways, but again, why take the time if you don't have to? So in this situation, if A is positive, then we have this dE y prime equals AY is called the law of natural growth. For example, population growth, where A would take into account the reproduction rate, and if you can quantify the death rate also, you can take that into account. Hopefully the net result would still be a positive constant, so the population would grow over time. But the idea is the change in population is going to be proportional to the population that's already there. Okay, if A is negative, then it's going to go the other way. Then it's law of natural decay. So a population that's about to die out. Or other situations, the amount of a radioactive substance. If you know the half-life of radioactive substance, then you can figure out what the constant A would be, and it would be negative. And you can model how much of a substance will remain at a certain time in the future. Okay. Now, all right, so that's for when B is 0. Generally speaking, if y naught is equal to minus B over A, whether B is 0 or not, then we get y prime is equal to 0. So what happens is, so minus B over A is one and only equilibrium solution. So y of t is just equal to y naught for all t. So this is the equilibrium. Okay. And what we also know is, now, what were the ways of classifying an equilibrium solution that we saw before? There were 3 classifications possible. Anyone? We would draw the phase line. Stable. Unstable. Semi-stable. Okay, so what we can figure out in this case is that this equilibrium solution is stable if A is negative, unstable if it is positive. There's no possibility for semi-stable here. So if it's negative, then solutions are going to keep decaying towards that equilibrium. If it's A is positive, they're going to grow exponentially in our direction away from that equilibrium. Okay. So, to recap what I've mentioned already, population growth. So dP dt. So P is a population. Is equal to difference of constants B minus D times P. So this is playing a role of A, and B is 0. So B would be birth rate, and D is the death rate.
Is that A on the bottom?
Yes. So in a general ODE, y prime is AY plus B, this is the A, and little b is 0 in this case. All right, so if you express the birth rate and death rate like as a percentage, so 0.01 for a 1% birth rate, then we know what the solution is based on the solution formula I wrote earlier. So it's the population, the initial population at time t equals 0 times e to the b minus d times t, where t, the units for t correspond to however you're expressing the birth and death rates. So, okay. Now here, this is again a very simplistic model. If you're studying a local population, you can account for other factors. You know, D, if it's an animal population, D could be accounting for natural causes as well as predation. If you're studying a human population, you might have additional terms for immigration or emigration rates. Anything else that could change population. Okay. Second one, radioactive decay. So dm dt is K times M. So M is the mass of a radioactive substance. So the mass at time t is just the mass at the initial time, how much you originally have, e to the kt. So K is going to be negative, since the substance is going to be decaying, it's going to lose mass over time. I'll show one of the examples later is if you know the half-life of the substance, so like a period of years, for instance, then we could use that to figure out what K is, get a value for it, and then from there figure out how much the substance there will be remaining at any time. Okay. And another is compounding interest. And lower level courses, you may have seen problems with compounding interest, where it's compounded annually, quarterly, daily, etc. We're going to focus on the case of compounding continuously. So the ADT is equal to R times A plus K, where R is the interest rate, A is the balance at whatever time, K, if you continue putting money in, so additional investment, so if T is in years, K would be the additional year that is being poured in. It's possible if you're just going to invest the money and just let it sit and not add anything to it, then K would be 0. Okay. So when the interest is compounding continuously, then we actually see exponential growth in the balance. Now, unless you get a really great interest exponential growth, but still. It shows, but it's a good illustration of why it's better to start earlier, say for retirement. You're putting in less now at an earlier age may be better than putting in more at a later age. Okay. All right. Now, the pages are all on this. Okay. Okay. Now I'll do some examples involving these kinds of applications. All right. So in the year 1900, the world population was 1650 million to 1.65 billion people. And in 1910, it had grown by a mere 100 million. Okay. So the idea is to take these two data points and figure out what the population growth rate is. So once you have values at 2 times, if you're fitting this to the first model over there, like dp dt is equal to a constant times t. So we just use this, where k is the b minus d from over there. So k takes into account whatever factors you're including that explain increase or decrease in world population. All right, so I'm going to call this p of 0, and we'll call this p of 10. So time will be measured in years. Okay, so the solution is equal to the initial value, 1650, so population will be in millions, times e to the kt. So the idea is we're going to use this additional information of population in 1910. So t is equal to years since 1900. So that's just a convenience. So that t equals 0 refers to whatever starting point we have, just to simplify the algebra. So we use this information to figure out what is k. So p of 10, which is 1750, that's 1650 e to the 10k, because we're plugging in 10 for t. So now we have this equation with only one unknown, k. So now we can solve for it. So what should I do to solve for k?
Well, I'm going to do the natural log.
Yeah, we're going to take the natural log. Before we do that, let's divide both sides by 1650. So 1750 over 1650 is e to the 10k. And yeah, now you take the natural log of both sides. So ln, so we need absolute value here, of 1750 over 1650 is equal to 10k. So now I have a formula for k, so it's 1/10 natural log of 1750 over 1650. So in general, if you evaluate if you know your solution at 2 different times, like these 2 times here, then what goes down here is a difference of those 2 times, so 10 years. And then you have a ratio of the population values. So the later one over the earlier one. Since this quantity in here that we're taking the log of is greater than 1, the log is going to be positive. Now at this point, you have no choice but to go to your calculator. And what your calculator will give you to a few decimal places is a pretty small value, 0.005884. Okay, so pretty slow exponential growth. Okay. So now when you have k, you can try to answer other questions about population using this model. So one question you might answer is, based on this rate of growth that we see between 1900 and 1910, how long will it take for a population to double from its 1900 level? So in other words, you want to solve this equation. So twice times 1650, so double the population, equal to the solution formula 1650 e to the kt, not for k, we know what k is, sorry. We're going to solve for t in this case. What can I do right off the bat to simplify?
By 2 times 1650 divided by 1650.
Yeah, we divide both sides by 1650. So what this shows is the time to double has nothing to do with what the population is now. It's really determined by whatever growth rate you have. So the fact that the population is 1650 now is irrelevant. So now we have 2 equals e to the kt. Yes, log is the next thing to do. So now I have ln2 is equal to kt, because the log and the e cancel each other out. That's supposed to be an equal sign. And now you can divide by the known value of k. So t is 1 over k natural log of 2. So when you have a simple model like this, a model like exponential growth or exponential decay, and there's no additional term here, like another constant term, you can use this to get the doubling time in the case where k is positive, or it's the time to cut in half if k is negative, which we'll see for radioactive decay. So now we can take the value of k from earlier and substitute it in here and figure out what t is. And it turns out to be 117.8 years. So what it's saying is, based on the data points we have from 1900 to 1910, the time needed for population to double from its 1900 level would be 118 years more. So in other words, this model predicted that the population would double from that level very recently, 2018, or late 2017. So obviously this model's a bit off. Yeah, so so the population was more than twice that level by then. So what happened was the interaction of the birth and death rates, this constant actually got larger later on. So, and generally such models cannot be expected to predict population growth over such a long period of time. It's something that has to be adjusted. Okay, so but here's how you can use information you're given about the solution. Like if you're given a solution at 2 points, how you can get the value of k, and then once you have k, you can answer other things like how long does it take for this to happen, or what time will this happen, things like that. So questions about solving for k, solving for t. These are the kind of things that come up in like the homework for this section. Okay. Now here's another dealing with radioactive decay. As you'll see, the algebra is similar. Okay, so the substance we're dealing with is radium-226, and it's known that the half-life is 1,590 years. So that's all. So if you have, say, 100 grams of radium-226, then after that long, that amount will naturally decay to 50 grams. Okay. So So M of T, which is the mass of radium-226, is equal to the original amount that you have at time 0 times e to the kt. So what we want to do is use this information about the half-life to figure out what k is. So if we plug in t equal 1590, so that would be m naught e to the 1590 k, but that's going to be half the amount. So it's going to be m naught over 2, whatever m naught is. So now we can use this to figure out what k is. So we're going to cancel the m naughts on both sides. So now we have e to the 15 is equal to 1/2. Like before, take the log of both sides to get rid of the exponential. So now we have a formula for k. It's 1 over the half-life times natural log of 1/2. Now, per less than 1 is going to be negative. So this will give you a negative value, which is what you'd expect because this is radioactive decay, or exponential decay, not exponential growth. So what happens when you work it out of your calculator? Actually, this is the same as minus 1 over 1590 natural log of 2, because when you take the log of reciprocal, that's of the original. So what you get from your calculator is going to be, again, a pretty small number. So 4.3594 times 10 to the minus 4. But yeah, if it takes nearly 1,600 years to decay to 1/2 the amount, that's going to be very slow exponential decay. All right. So now that we have k, we can answer questions such as this. If you have a sample of 100 grams, you want to know how much will remain after 1,000 years. So in that case, all you have to do is just plug in t equal 1,000. So that's going to be 100, the initial amount. So this is your m naught, times e to the...
Is that negative?
Yes, it should be negative. Oh, I see what happened. In my notes, I had the absolute value. Okay. All right. So then, this value for k nice straight arrow there, gets plugged in for k. So then you can go ahead and work all that out. And you need your calculator for this. And what you get is roughly 64.6655 grams. So you still have much of a substance. Now, it's a good idea to do, if you can, like a sanity check on your answer, because who knows what mistake might have been made, like punching things in your calculator, etc. Because we're finding out how much is left after 1,000 years, which is less than the half-life. So right off the bat, because that amount of time has not passed, you should have more than half left. So if you got an answer that was less than 50 grams, you know that something went wrong. So little things like that you can do to check, does your answer make sense? Like, what if your answer is supposed to be quantity that is inherently positive, like area or volume or density, things like that, and you get a negative answer, and you know that something went wrong. And then another question we can answer is, how long will it take for 100 grams to decay to 30 grams? Now, before we even do anything, we can actually ballpark the answer. Because so we're starting with 100 grams, we know it would take this long, 1590 years, to decay to 50. How long would it take to decay to 25 grams? That's an answer we can get without any. Yes?
Another 1590.
Yeah. So every time 1590 years elapses, the amount is cut in half. So after 1590 years, you're at 50. After another 1590 years, so 3180 years, it will decay to 25. So the answer should be somewhat less than 3,000, just ballparking. And if you kept going, you would cut down to 12.5, 6.25, etc. Okay. So what we can do is solve this equation. M of t, 100 e to the kt, is equal to 30. Again, the known value of k can be substituted in. But, so if we divide both sides by 100 and then take the natural log, then what we get is the time is equal to 1 over k natural log of 30 over 100. Now, again, log of a number less than 1 is going to be negative. But k is also negative. So the end result is going to be positive. So once again, you turn to your calculator. And what you get is 2,761.8 years. So sure enough, it's between 1 half-life and 2 half-lives, which is expected because the amount is between 50 and 25 grams. And it's closer to 2 half-lives. Right. So the idea is you use whatever information you have, like the initial value and the solution at one other time, and this is what happened in both examples. That enables you to solve for k. And then once you have k, then you can figure out how the solution behaves like at other times. How long does it take for this to happen? What's the solution at this time? Etc. So questions about this example? So in general, if y of t1 is given to be y1, which may be an initial condition, y of t2 is equal to y2. Then you have y2 is y naught e to the kt1. Oh, sorry, that's y1. y2 is kt2. So then what happens is you have, if I divide this equation by the first one, y2, y1, e k t2 minus t1. So that gives you a general formula for k. K is equal to 1 over the difference in times, natural log ratio of the solution value. So this is what works in all situations. When you're given the solution at 2 points in time, how you can get k. So it applies for population growth rates, k. Anytime you have a solution of this form, like for a dm dt is equal to km. Okay. Now, this example, I'm going to recall a previous example where we had a tank that has solution with dye in it, and flowing into the tank at a rate of 2 liters per minute. And then we have solution with the dye in it leaving the tank also at a rate of 2 liters per okay. And at time 0, we have 200 liters total of solution. So 200 liters is what's in the tank, and it will remain at that amount for all time because the inflow and outflow rates of the water solution are the same, are balancing each other out. So that works out well for a shark. The concentration of the dye in the solution is equal to 1 gram per liter. Okay, so if I let Q of T be equal to the amount of dye in the solution in grams, then we have dQ dt is equal to inflow rate minus outflow rate. Now, there is no inflow of dye because it's pure water that's coming in. We just have dye going out. So that's going to lead to a minus. So as far as how much dye is leaving per minute, so we have, okay. So now since Q is in grams, the derivative with respect to time should be grams per minute. So what we have here is the liters will cancel out. We're going to end up with grams per minute. So another way of looking at it, actually this might be more intuitive. Grams per liter is the concentration of dye at the current time. And then we have the amount of solution leaving the tank. So that's 2 liters per minute. So then the liters, in terms of for units, the liters will cancel out, and we're left with 1 over 100 times Q grams per minute. So it turns out to be minus 0 Q. So that was the ODE. So it's the same kind of ODE that we've been dealing with, where this is your constant, so your A, and B is 0, being minus 0.01. So your solution, using the same old solution formula, is your initial amount, e to the minus 0.01 t. Now the initial amount, 200 liters, and your concentration is 1 gram per liter, so the initial amount is going to be 200 grams. So 200 e to the minus 0.01 t. So that's how many grams of solution, grams of dye you have at any time. So Now, the question to answer is, how long will it take the 1% of the initial value? So, because it's exponential, the exponential function is never zero. The solution will never, ever be completely free of dye. It'll just have an incredibly small amount if you wait long enough. So, since there's 200 grams of dye initially, you want to find out how long it takes for there to be 1% of that. So 2 grams. Q of t is equal to 2 for t. So if we have 2 to e to the minus 0.01 t. So if I divide both sides, I have 0.01 is e to the minus 0.01 t. So here, really, this is what you want. This is 1%. So however much you started with, the amount of decay to 1% of that amount is the same. So really, you're just solving this. So you don't even need to know the initial amount to answer this question. It's a percentage that matters, and that's what goes here. So this is percent remaining. It's like the question involving half-life. I wanted to know, I said it's equal to 1/2 because the substance is decaying to half its amount. So now you can go ahead and solve this by taking a natural log of both sides. So natural log of 0.01 is equal to minus 0.01 t. So we're going to have negatives and negatives making a positive. All right. Okay. And once you grind it out in the calculator, you get 460.5 minutes. So it's going to take nearly 8 hours to have 1% of that initial amount left, regardless of how much that amount is. Which reminds me, I think it was nearly 10 years ago when I was wincing over seeing a student who was in my office use a calculator to figure out how many minutes there are in 8 hours. And if I would not have felt that way if I'd realized what students were going to be using calculators for that are far simpler than even that, such as determining if 4 is greater than 3. I'm not exaggerating. I guess it's a generational thing. Like when I was in school, a calculator was like the worst thing to have, pretty much. So anyhow, questions about how we get the time value in this case. So it's a good idea in these examples for anything else, to look through these examples and see, even though they're for different applications, the ODE always has the same form. So then you can, so the mechanics, the algebra, unfolds pretty much the same way, answering whatever questions are asked about how a solution behaves. All right, now I have one more. That's a financial example. Okay. So this is the ODE question, where S is the total amount of an investment at time t, after t years have passed. R is since it's an investment, it'd be a rate of return. And then K is additional investment per year, since t is in years. Okay. Now, the same solution formula applies.
So is that RSTK or RS plus K?
That's a plus. Those are my t's. The distinguish. Okay. So S of t is S naught, the initial amount of the investment, e to the kt, plus e to the kt minus 1 all over k. No, that's not right. These are r's, not k's. Thinking of a wrong example. All right. And k goes here. All right. All right, so it's r that determines the actual rate of growth. Okay. So now, for our first scenario, I'm going to assume that R is 7.5%, 0.075. And I'm going to assume that the initial investment is 0. So all you're going to do is you're going to dump K dollars in every year and have all of that grow with this rate of return. And what we want to know is how much should we put in every year? What should K be so that the total amount is $1 million at t equals 40. So after 40 years, we've dumped in K dollars a year and have a balance exactly $1 million at the end of that 40 years. Now, so if we substitute in all the information that we know, well, so this term won't be here because we're starting with nothing. So I have e to the r, which is 0.075, times 40 for t, minus 1.075, times k, is equal to 1 million. Now, the thing is, everything in parentheses here, all that's known. So we just grind that out on your calculator. So we get k is equal to 1 million times 0.075 over e to the 0.075 times 40 minus 1. This number in parentheses turns out to be 19.0855. So when you work out all of that, what you get is roughly $3,930. Okay. Now, that's that much every year for 40 years. So, the total is actually you actually dumped in is equal to this amount, 3,930 times 40, which is equal to 157,200. So if you get that rate of return per year, 7.5%, this amount will be worth $1 million after 40 years. So questions about that one? Now, if I pose a different question, where K is known, if I say I only want to dump in 2,000 a year, and T will still be 40. Now the unknown is the rate of return. So what should R be so that my balance after 40 years is still going to be $1 million? Now it's going to have to be, I'm going to need something larger than 7.5% because I'm putting in less. So what we have here, again, this term I don't have. So I have e to the 40 times r minus 1 over r times 2,000 is equal to 1 million. So that is the equation I now have to solve for r. Now, I'm not going to give a question like this on homework or a test because good luck trying to solve that algebraically. It's not going to happen because we have the r down here and it's also in the exponential. This is an equation that would have to be solved numerically, or if you have a graphing calculator, you can use that to try to ballpark it. What you would get is 9.77%. It doesn't have to be that much higher than before. So a little more than 2% higher will cause this amount, which is only a little more than 1/2 of a previous amount, to still get $1 million after 40 years. Okay. But just to give an idea of the kind of questions that come up when you have a solution formula and basically you're given all the parameters but one in each scenario, and you're trying to solve for that last parameter. It could be R or T or K in this case, or possibly S naught. Like, suppose you didn't have this term here, and the question was, if you just want to put down a certain amount of money all at once, and find out what the rate of return should be, so that after 40 years you get $1 million. In fact, because there's time, I'm going to go ahead and answer that. So if I have K equals 0, so we're not putting in any money every year, we're just putting in one amount down all at once. And T is equal to 40, and S is equal to 1 million. What should S naught be in this case? So I'm solving S naught e to the, oh wait, I need, okay, I want that same rate. Like I said, I need to specify all the parameters except one. Okay, so that 0977. So S naught e to the RT. So 40 times 0.0977 is equal to 1 million. So what I need to do is solve for S naught. So S naught is going to be $1 million times e to the minus 40 times that rate of return. Okay, so keeping in mind that in this scenario, we're putting in 2,000 a year over 40 years. So we're putting in 80,000 in total. But if I work out what this is, okay, 0.0977 times 40. Right. Okay. And then I take the exponential of that times 1 million. Okay. So it turns out that the initial amount, 20,000, is roughly $20,081. So same rate of return over about 40 years. You can either put down 20,000 at the beginning, or you can put in 80,000 total, but 2,000 a year over 40 years, but 80,000 your total outlay. And either way, you get 1 million at the end. The reason why this amount is so much less is because now all of that is experiencing exponential growth over 40 years. Whereas here, the first year's amount, 2,000, that will also get that much exponential growth over 40 years. But each $2,000 dollar you put in after that is going to experience that much less growth because it's sitting there for a shorter time. And now we can see what an enormous difference that makes. So if we're able to put in more initially, that works out a lot better. Okay, so those are all the examples I have. So again, look at the practice test and its solution. And we'll talk about that and problems on Wednesday. Stick around if anyone has any homework questions.